have place the broadening of peaks, and in the case of KDP crystals, there are no changing in it. We assume that in the case of the heating up and cooling down of the DKDP samples with a small number of temperature cycles, the corresponding transition heats might be written in the following manner, where delta H TR is the true value of thermal effect associated exclusively with rebuilding of structure of ideal DKDP crystals. Delta HP is the heat of plastic deformation or the electric losses in the first thermal cycle associated with the friction of domain walls because of low mobility of domains in DKDP crystals. The term delta HL will be heat part of elastic energy of domain walls. Since the heat delta HP and delta HL are released both on heating up and cooling down of the samples, they have the positive sign. With a large number of thermal cycles, the mobility of domains in a sample becomes practically equal to zero. In such a case, the sample is overloaded by non-equilibrium point defects and dislocation localized on the domain boundaries. As a result, the energy delta H plastic, which has already been realized due to friction, now must dissipate owing to the formation of cracks in the sample during plastic flow. Therefore, the value of delta H plastic bears its sign to minus, which denotes the absorption as compared with that of delta H plastic in the system of KDP. With regard to models, we assume those values to be the same, since they are determined by the electric losses in the crystal, which are preset by value of spontaneous polarization due exclusively to nature of ferroelectric itself. Take into account the remarks thus made for a large number of thermal cycles, the system of equation transforms as follows. Hence it becomes easy to evaluate delta H plastic, that is the energy of plastic flow, the electric losses in DKDP crystals. And we can take the energy of plastic deformation 0.33 joules per grams. Assuming the contribution of delta H plastic will be in the initial thermal cycle to be the same as that with N more than 80. And we obtain 0.16 joule per grams for temperature cycles 2, 3. In the case of KDP crystals, a similar system of equations of the energy balance will have the following form, where delta HD is the sum of energies of plastic and elastic deformations of crystal. And we see the 0.95 joules per grams. This means that in the KDP crystals only the absorption of energy by the domain wall is absorbed. It is indicative of the absence of internal energy source. Now, if in equation 3, the term delta HD were taken with sign minus, which presuppose the presence of only energy of plastic deformation or dielectric losses, then it would still denote the absence of elastic energy evolution. Therefore, in the case of crystals DKDP, we see evolution of energy of plastic deformation, and in the case of KDP crystals, we not see this energy. The proposed channel of evolution of elastic energy is the next. We can propose that the coherent nuclear reactions that led to the energy evolution can take place. There are reaction with tritium, but it is very small, containing of tritium. And then the reaction with virtual neutrons in potassium and phosphate. This is a Feynman-like diagram for proposed coherent processes of heat production or domain wall elastic energy evolution. It can realize where the concentration of elastic energy of domain walls can take place, where L domain of DKDP in unexcited and excited states respectively. Thank you for your attention. Давай.
What's the question? Ben.
There's one critical question with regard to your final diagram. Have you seen any isotope shifts in the crystal?
Isotope shifts?
Yes, in the crystal.
We cannot to see the isotope shifts because the
Half decay.
because half decay of potassium is very many time, and we cannot see the isotopes of this species. We see only tritium and neutron production in this case.
Okay. No other question? Thank you again. Go back to we go back to Christian. We're just going to show you us about tritium generation in metal hydrogen systems. But the pattern could be revised.
I noticed the organizers have given me the option to change the title. So I thought I will just added this last night. My talk will cover, actually we have 3 or 4 papers in this meeting, and I would like to very briefly introduce you to the summary of all these papers. So in the second part of my talk, I would like to deal with the burst neutron emission work, and in the first part I will discuss the tritium generation in metal hydrogen systems. The various techniques which we have used for loading gas or plasma, I'm talking about deuterium or hydrogen gas or plasma into metallic samples, over the years have covered these. In the beginning, way back in 1989, we first observed tritium in radio frequency heated titanium targets, and I emphasize the RF heating because we sincerely believe that played a very important role in the production of tritium. Subsequently, conventional pressurized deuterium gas was loaded into foils and discs, and that gave us tritium. And in 1990, we reported the probe meeting the observation of tritium in titanium chips, which were subjected to liquid nitrogen cooling. This is very similar to the work of Mallove in Los Alamos, except that instead of looking for neutrons, we look for tritium. We got some very fascinating radiographs, and if there's time, I would like to show that at the end of my talk. And then we had the first observation of tritium in a plasma focus loaded titanium anode, and that particular anode is even today giving patterns, very similar patterns, and indeed that gives us a hint as to the stability of the deuterium in titanium system. And then we observed some tritium in so-called aged titanium deuteride targets, very similar to the work of the first speaker this morning. And all this was old work. Everything about the dotted line was reported in previous meetings. I will try to very quickly flash through some slides if there is time at the end of the talk. However, in today's meeting, the new work is we have been doing a lot of experiments with self-heated wires. We have 3 different groups, one using nickel wire, one group is looking into titanium wires, and a third group into palladium wires, and I will discuss some of those. We have initiated the classical discharge type of experiments with wires, and we have also looked into loading targets, protons and deuterons using ion implantation, but I will not talk about it in today's meeting. So that is the broad plan. I will very briefly flash. This is an old slide I have. Everybody knows all about tritium, half-life and number of atoms in per becquerel, etc. The only point of relevance perhaps here is the energy being only 18 keV. The range of betas in titanium is 1.5 milligrams per centimeter squared, which translates to about 3 or 4 microns in titanium, and in the case of palladium it's even lower. So if betas are there in solid samples, it is only those betas in the top 1 or 1.5 microns which are going to survive coming out. However, in the case of titanium and possibly in the case of nickel, these 18 keV electrons are able to excite the X-ray, whose range is a little higher, something like 20 microns. So the point I wish to bring out in this slide is that by measuring the X-ray counts and the ratio of X-rays to betas, we can get an idea of the depth from which the tritium betas are emanating, and that is useful. Unfortunately, tritium betas cannot excite the 22 keV X-rays in palladium, and that's one of the problems of detecting tritium in solid palladium targets. Only the betas have been measured directly. Measurement of tritium contained in samples. Of course, this is just a quick summary. Everybody knows that if it's a solid phase, I'm going to come to that. There are various techniques we can use. However, if the tritium is in liquid case, the common method is liquid scintillation counting. If the tritium is in the form of water vapor or moisture, for example, a very common accusation that is that many laboratories have tritium in the air, and it is this that gives contamination. So this is a very common technique known as the cold strip method. Just a bottle of cold water, the tritium accumulates, that water is collected and counted. And if it is in gas phase, of course, ion chambers and flow counters used, and we don't have that much experience in this as yet, but the Los Alamos group and I think other people have shown that. What are the techniques employed for in situ measurement of tritium in solid samples? The first technique we adopted was autoradiography, which a lot of people have since then been doing. I mentioned about the measurement, direct measurement of the K X-rays, particularly in the case of titanium. It's at 4.9 keV. So if a sample has betas very close to the surface, we can measure it directly using a sodium iodide detector or a germanium detector. If the sample is kept in a windowless counter, gas flow counter, we can count the betas directly. We have done that in some cases. And if the activity is very large, of course, we can stick it into an ion chamber and directly measure the current. This dotted line, above the dotted line is techniques we have reported on before. However, in today's meeting, I would like to make some brief remarks on two new interesting techniques which we have run into. One is what we call a thermoluminescent phosphor image plate method, and this of course is a commercial unit, and the second is directly imaging individual nuclear particle scintillations using an image intensifier tube. I would like to report on only these two in today's meeting because they are sort of interesting and novel. Autoradiography using a phosphor imager. Now this is a device which is marketed by a company called Molecular Dynamics, Sunnyvale, California. The system costs more than $100,000, but our life sciences department in Bath has recently obtained one, and it was very convenient for us, and they were kind enough to let us use it. These are based on use of reusable image plates, which basically work on the principles of thermoluminescent detectors. Actually, it's made of very fine crystals of barium, fluorine, bromine, European 2 with an organic binder, which is spread in the form of very thin coat on a backing. Radiation such as X and gamma rays, betas, ultraviolet, etc. can excite the European plus to the conduction band. This forms a sort of a latent image which can subsequently be scanned using a very fine helium neon laser beam. Photons are emitted, which is then collected by fiber optics, photomultiplier tubes, stored digitally, and thereafter, since it gets into your computer, you can do wonderful software image processing techniques. So this is very convenient, and such an image plate technique, expensive though it is has a number of advantages. Advantages of phosphor image plate technique over conventional film radiography: it is faster by a factor of 10. Days of exposure are reduced to hours. 50 to 100 times more sensitive as compared to an X-ray film. It has a much greater dynamic range. That's the most interesting point. Whereas an X-ray film has a dynamic range of only 1:300, these plates are 1:100,000. So that even with very low intensities, we are able to get a nice image. Of course, instant processing and readout and display, no chemicals, no darkroom. The sample can be irradiated. Within 3 minutes, we can read it out. Data is directly available in the form of digitized and stored for quick access, retrieval, etc. And as I said before, very powerful image processing and display techniques are available for manipulating it. Unfortunately, these crystal, the image plate, they have put a very thin coating on the surface to protect it, and I think quite a bit of the tritium betas are cut in there. This is something that we were a little bit disappointed with. All other radioactivity, carbon-14 and so on can be done, but even then if there are K X-rays, it goes right through the coating, and we are in the process of evaluating the sensitivity of these techniques. This is a plot, a comparison of the sensitivity of these techniques. Now this is for the image plate storage phosphor technique, and this is the conventional optical intensity versus the disintegrations per millimeter squared, and this is at a log scale. So when I say here, when this thing says it is 10 to the 3 disintegrations, 3 disintegrations, it essentially means somewhere between 10 to the 3 to 10 to the 4 disintegrations per millimeter squared are adequate, integrated over several days. So that it's less than a becquerel per millimeter squared can be detected by these. That's all. This is a 17-hour exposure with an X-ray film as compared to 1-hour exposure for the optical storage phosphor. This is the same thing, slightly better. Here is 1 hour versus 16 hours, log disintegrations, the same thing. There's no new information in that. Now, if I can operate the slide projector and show you some slides, I think no other speaker has used it before. Let me see. What do? Switch it off here? Okay. Thank you. This is the image plate. Actually, this is the top. That's a sample we have kept there. This is a titanium disc, which is titanium deuteride. And do I focus it or did I don't have anything here? Maybe there's something. This.
Oh, they're doing it.
Okay. Thank you. This is just next one, please. I thought there should be one more. But anyway, this is the system as a whole, marketed by molecular dynamics people. And right there, it's like a Xerox machine. You just keep the plate inverted on that, and the rest of the stuff reads it, and you get the image flashed on there. Beautiful system for radiography. Next. Now, this is the image of a few samples. This is palladium. Now, let me read out for you precisely what I have here. This is a 22-hour exposure, and these two are titanium deuteride samples. These are what we call the aged targets, which we showed 5 years ago. They have tritium has come in there, although when it was manufactured, it was purely titanium deuteride. These two are titanium loaded palladium wire, tritium loaded palladium wires. They are done purposely loaded tritium in it through electrolysis to find out the sensitivity of technique. These are not cold fusion produced, but these we believe are cold fusion produced tritium. Next. Now here is yet another sample. Here is a wire, you can see that. And there are a few more. Carefully see. There are altogether 4 samples here. These are titanium, palladium, nickel. Thank you, that's much better. Titanium, palladium, nickel, and zirconium. All of these loaded electrolytically, and this is probably a 5-hour exposure. And it contains, each of them contains a few becquerels. Total radioactivity in each of them is just a few becquerels as measured by a beta counter. Next one, please. Now, this is just a 2-hour exposure, and this again is a few becquerels. This is palladium here, and that is nickel loaded with tritium. And here, as I said, we are trying to find out the minimum sensitivity of detecting tritium. Next. Now, this is our old titanium anode, which we had projected at the Salt Lake City meeting, which contains plenty of, I think, about 400 microcuries of tritium. And surprisingly, the image we get after 5 years is very similar to what we had 5 years ago. But this is for the first time we have tried it on the image plate technique, and this is a 14-hour exposure time. Thank you for those slides. I'll proceed with it. Now I'd like to come to the second novel technique we use for imaging. This is imaging of individual nuclear particle scintillations. And now this looks complicated, but the whole physics is right there. All that we have is a source of nuclear particles in that green line, and slap onto that a scintillator. In this particular case, you can use zinc sulfide or calcium cesium iodide and so on. And right there it produces scintillations. And if some of you remember, Rutherford is supposed to have seen that under a microscope. All that we did was stick an image intensifier tube on top of it. In fact, we have in this particular slide 2 image intensifier tubes, each with gain of more than 30,000, optically coupled. We look at it through a CCD camera, and then we have a frame camera and software, and the whole thing goes on to your PC, and we are able to even record it on a video tape recorder so that we can play it back. But basically the physics is right there, and we are able to, the important point is individual scintillations. Each alpha particle decay or each beta or even an X-ray photon can be detected. Can I have the slide, please? Now, this is a handheld, battery-operated nuclear particle scintillation viewer. So, if you have a piece of coin which is radioactive, you can stick it in there and have a look at it. But the problem here is the scintillations are produced in the decay, and the eye cannot quite easily integrate. So it's much better to stick in a camera there. You can just directly photograph it using a Polaroid camera, give an exposure of about 5-6 minutes, or as you depending on the, or of course more sophisticated, look at it through a CCD camera and go on to the next one, please. Now here is the same thing. I think this is directly done with a Polaroid camera with this battery operated device. These each one slightly out of focus, but each is a single disintegration. So this is an alpha scintillant. Let me read out for you precisely what it is. This is a ring-shaped americium-241 alpha source, and this is what we get in a single frame of 40 milliseconds. The frame grabber time duration is 40 milliseconds. Next one, please. The same thing, this is several frames integrated, maybe about 1 or 2 minutes, several such 40 milliseconds frames. So this is the ring source of alpha particles using this method. Next one. This is a tritiated palladium wire, electrolytically loaded, and the original electrolyte probably had a few hundred nanocuries per ml. But here again, we are studying the sensitivity of measuring this. Next. This is a tritiated titanium wire. I apologize for the poor. Actually, on this thing is much sharper. This is slightly got out of focus in photography. Now, what we are trying to do is we are trying to find out whether we can image individual beta particle scintillations from the tritium. Now, we were very happy with this until in the last minute we found that some of these wires, we stuck it on a surface barrier detector, they also had a little bit of alpha contamination. The activity ratio was just 1%, but the doubt arises whether what we are seeing here is the alpha or the beta. Studies are on, but probably it could be the alpha. Next one, please. These are thermoneutron scintillations using, this is for 40 milliseconds. In this case, they are using a boron-10 converter plate. The thermoneutrons interact with the boron-10, and those alphas are captured on the zinc sulfide, which is then viewed. And as I said, this is again a single 40 millisecond time. Next. This is just to show the power of the technique. This is a neutron radiographic image using an Ne425 scintillator, which already has lithium-6 loaded. But this is probably the first time somebody has taken a neutron radiograph with just a plutonium-beryllium source of about 10 to the 6 neutrons per second. This laboratory source, but this is just a screw, a plastic screw. This is just to show the power of the technique. Thank you very much. So these are the two new techniques for viewing radioactivity. Let me come on to the actual papers. In this meeting, we have 4 papers. The first one is titled Evidence. There are posters on all of them somewhere in the hall. Evidence for tritium generation in self-heated nickel wires subjected to hydrogen gas absorption-desorption cycles. This is done in the Chemical Engineering Division. Protocol for controlled and rapid loading, unloading of hydrogen deuterium gas from self-heated palladium wires to trigger nuclear events. This is done in the Neutron Physics Division. The third is observation of high multiplicity bursts of neutrons during electrolysis of heavy water with palladium cathode using the so-called date-time filtering technique. And finally, this was a post-deadline paper which the organizers were kind enough to accept. Preliminary results on the variation of electrical resistance of a titanium deuterium wire than the Technical Physics Division. So let me see, depending on the time, how much I can cover. How am I doing? I don't know who is it. Thank you. Oh yeah, I already given the title, so I don't need that. Now this is a very simple laboratory device. All that I want to show you is here is the wire, the little glass cell, and the nickel wire is sealed inside here, and electrodes, the connecting wires are available. We can connect it to your power supply to pass current of 1 or 2 amps. We have a silicon oil manometer connected to the glass system, hydrogen cylinder, vacuum unit, and mercury manometer to pressure, etc. Very simple. Can I have the slides at this point, please, for this experiment? So this is the setup here. This is the gentleman who has done this work, and somewhere here is a glass cell. If you can see it in focus, can you focus it slightly, Peter? This is the oil manometer, etc. Well, if you cannot, we'll proceed to the next slide. Next one, please. There you see the cell proper. Here is a nickel wire which is glowing at this thing, and you can fill it with hydrogen, and over a period of hours we can measure the pressure drop and see the actual absorption. Similarly, you can evacuate it and take it to glow hot conditions and find out how much gas comes out. So we are able to monitor the absorption, desorption characteristics. In this experiment, we were trying to reproduce, oh wait a minute, there are more, I'm sorry. We were trying to reproduce the, please, next slide please. The Piantelli experiment. Now the same cell, this is a double wall tube, and water comes in and goes out, and we can measure the delta T. Here is 25.4, one of the thermocouples here. RTDs, I guess, and it's a very neat way of measuring. So we were surprised that this has it captures about 95% of the heat produced. So the efficiency is quite high, and we are all set to measure excess heat if it's produced. But so far we have not seen any excess heat. Next one. This is for the nickel wires. After several cycles of absorption, desorption, were dissolved in nitric acid. This is the micro distillation setup. And after distilling the dissolved sample, it is then counted in a liquid scintillation spectrometer. Anything more? Okay, that's all for that. Thank you. Now, these are some of the results. I'll try to quickly go through. This is the VI characteristics of nickel. Now, the only interesting thing here is I haven't come across such a thing. When we plotted the voltage versus current, we found a rather interesting behavior. Above the Curie point, this was absolutely straight. Normally people plot the resistance versus power in or whatever it is, but when you plot it as a VI characteristics, this particular what I call the incremental resistance ratio turned out to be a remarkably constant thing above the Curie point. This was in vacuum, the same thing we find when it's filled with hydrogen gas, the same kind of behavior at 51 centimeter pressure. Now this is the integrated absorption of hydrogen and nickel 30, February 9, so on, net absorption. Now this is the first point, overnight absorption, about 50 centimeters of oil. Then you keep it for another 8 hours of desorption, some of it comes out, then again it absorbs, desorbs and so on. So this is the work of over a period, and systematically the amount of hydrogen goes in that has gone in, and the net amount that is supposed to be in the wire is shown here. Now conversion of centimeters of absorption into milligrams or micrograms of hydrogen was done knowing the volume of the cell, which is a very simple technique, and it was double checked using palladium wire. The same technique was used with palladium. In the case of palladium, we are able to measure online the resistivity by the Nekober curve, and we were very happy, and using the same thing when we convert this into the nickel to hydrogen ratio, it was truly astronomical. And we couldn't believe it. In the literature it says nickel is not supposed to load more than 10 ppm. However, finally we found a group in Bath who have inert gas diffusion cell. I mean, they dissolve, melt the whole thing and get the hydrogen out and measure it. And we were surprised that did not show the amount of hydrogen we were suspecting. So there is some controversy of what is exactly the loading. This is the quantum of hydrogen absorption in several wires that have shown tritium. This is the last column, centimeters of absorption. This particular wire, nickel 27, really absorbed, even right from day one, its absorption was remarkably very nice, and that is the one that gave us maximum amount of tritium. In recent wires, all these three have shown tritium. I'll come to the tritium results in a minute. 5 minutes? Whew. I covered only one paper. This is the total tritium activity. You can see 15, although 6 out of 9 wires have shown tritium. But in several wires, the tritium production, they are cut into 3 or 4 bits. Some bits showed tritium, some did not. But the later wires, all the 3 bits, you can see 31, 32, 33 have shown tritium. So I think I'll have to skip the rest of this paper and skip the second paper. protocol of hydrogen loading and all that, I'll probably have to go to the neutron measurement with just 5 minutes. Now, in the dead time technique, the principle of the dead time technique is here we have a series of pulses coming from a neutron detector. If there are 3 pulses that are coming close together and we pass it through a dead time technique, following this green one, which is the first pulse, the remaining 2 pulses are cut off. So we are able to separate it into the leading pulses and the following pulses, and it is these which can be measured by the suitable techniques, and analysis can be done. So I'll have to only jump to the results here. The kind of, it's all in posters. For example, this is the frequency distribution of pulses in 5-second intervals. How many times we got 5 pulses during the whole 5-second interval. So this is for the case with no cell. This is the actual number we got over a period of 15 days. This is each is for 1 day. And NPD stands for the number you expect if it is Poisson distributed. You can see that even for the background cell, there are some events which are beyond Poisson, probably due to cosmic rays and so on. But this number, you never see a single case where you have 6, 7, or 8 pulses. I'll go straight to the case with deuterium. This is the case with deuterium. You can see several instances where there are 7 or 8. This is in 5-second intervals, and now we have not even used the dead time filter data. This is just directly the counts as you obtain, and it is fed. A similar analysis has been done now with the dead time filter data. So I will now stop showing you figure. Now this is day-wise plot during the experiment. We started with 15 days of background, then 30 days of D2O plus LAOD. This is a Milton-Roy cell, and following that, about 15 days of hydrogen. Now this was, in hindsight, is probably not a good idea. What you do find here is a tendency for these counts. This is just average counts, nothing very fancy as yet. The average counts are decreasing. Average counts is higher than background. This is the cell was simply you replace the H2O plus D2O by H2O. And I have a feeling it has been taking several days for the deuterium inside the lattice to actually change. So the effects we get are not due to hydrogen, but probably due to the deuterium, which is still remnant there. I will go to the burst neutron results. These are the burst counts in 100 microsecond intervals. I'm sorry. This is without cell. This is with the cell. This is the number of burst counts we got over the whole day. This is per day. This is the first day, second day, and so on. Now here again, it very clearly shows that on replacing the D2O by H2O, it took for some time for the deuterium to get replaced. And I think I should probably come to the conclusion at this point and leave some time for discussion maybe. Oh, there it is. This is the burst counts results. Very clearly, the multiplicity of counts per burst and number of such bursts over a 30-day period integrated. You can see that when there is no cell, there is not a single event of 4 or 5 or 6 counts. Whereas with deuterium, with heavy water cell, it's very clearly the presence. The conclusion therefore is when you have a cell sitting there, even though the average count rate about the neutrons produced may be small with respect to the background, you can clearly say that whatever is happening, the cell is putting out neutrons in bursts. If you convert the number 4, since the efficiency of counting was about 10, this means actually approximately 40 neutrons are produced in a burst. This is 50 neutrons, this is 60 neutrons, and some events of 70 also. So what we come to the conclusion is in cold fusion, there might be Poisson distributed counts which are coming out one at a time, maybe of 2.45 MeV, but clear evidence that bursts are produced, and this can be picked out very easily because in the case of bursts, absolutely the signal to noise ratio is extremely high, and the dead time technique gives us an opportunity to do that. I think I should stop here because there's no point in my going through any of the others in a short time. Thank you very much.
Your questions?
particular experiment was a Milton Roy cell, palladium in D2O. Palladium has a very large, this particular cell is a very large surface area of 300 centimeters square. This is a commercial Milton Roy cell. But I would like to add that subsequently we have repeated the experiment with a 100 micron diameter palladium wire electrolytic cell, and that is also showing us. I have no time to tell us that. It's very clear that burst neutrons are produced from almost all the cells. Well, all I can say at this point is it's kind of I know from the centimeters of oil manometer measurement, it has loaded a large amount. But by the time the sample reaches the laboratory where they dissolve it and take out the hydrogen, it seems to have gone. So we don't know whether it is there. That's what I feel. So we have to work it out. But if it has really loaded as much as this thing, it comes to even more than hydrogen, more than palladium.
Oh, yeah.
This is unbelievable for me.
Essentially, it goes right to a beta phase. When it goes in, if it gets that.
Well, no literature, no paper we have seen ever mentions that nickel is a prolific absorber. So I would like to reserve my.
Oh, no, that's yes, the old list.
You have to go back to the old book.
Well, no, I would appreciate any participant if he can give us some references because we are totally confused on this particular issue. But all I can say is tritium. No matter what the loading, there is tritium there. That's all. With nickel hydrogen, mind you. This is not deuterium.
I mean,
Thank you.
the thing about nickel is it's a layer.
Thank you, yeah.
Do you ever see phosphor plate images or scintillation data from wires that have been just cut from the starting material or?
No, we tried that. No, we made sure of that. In fact, maybe, can I just show one slide? Is there time to show one slide? Do I have time? Can I have the further slides, please? How much time do I have? 1 minute. 1 minute. Can I hear the receipt? No, there was one particular, if I can quickly flash through some of the slides, please. That was there. No. Oh, go right through, please, right through. We've gone through all that, yeah. Next. Go right through. Keep going. This is the palladium wire. Please proceed. Yeah, please, that's the one. Now, I would like to just flash this. This is an autoradiographic image of, this is a conventional X-ray film of a palladium hydride wire. Now, if there is one thing that is reproducible in this palladium business, it is the autoradiograph to get with palladium hydride. And this is something which has been puzzling us for the past 5 years or 3 years maybe. This is just hydrogen, and some palladium hydride is luminescent in some sense of the word. Can I have the next one, please? We've been trying to understand what is it that the radiation. Now, this is the same wire. In the second, we have two such films, one behind the other. For those who say that this image formation is due to a chemical reaction between the hydrogen and the X-ray film, this tells us this is the second X-ray film. The X-ray film itself is a fraction of a millimeter thick. So this, in some cases, this radiation seems to go right through a sheet of paper. Next, please. Can I go through?
Loading ratio for that.
Now, pardon me?
Loading ratio.
Well, as they look at this now, with the self-heated wire method, we can now precisely control the loading. We can go to 0.1 loading, 0.15 using the resistivity ratio. Look at this interesting thing. If it's out of focus, this is the place where the wire was held between screws. But it never saw the hydrogen gas directly. It is obviously being diffused. This is the image. In this particular case, we get even with a loading ratio of 0.1. Amazing. And if that is 0.1, this should be even lesser. So what is it that is causing autoradiographs with plain palladium hydride is something that they are not understood. Next, is there something else?
And that's hydrogen, not deuterium.
Just hydrogen.
Hydrogen.
Yeah, not deuterium. So this is a warning. Those who think they have seen tritium just because they get autoradiograph in the case of palladium should think twice, because in the case of palladium, even palladium hydride gives 120% reproducible, every single wire. Thank you.
Thank you very much.
I'm sorry that I have to go.
Next, the gentleman from CNR5 the batteries differentiation from pencil and or stated non-equilibrium states of the rats.
I'll locate in 1 minute.
Well, ladies and gentlemen, I'm not going to present extraordinary results about about neutron detection, but a set of experiments which we have performed in Padua since a couple of years, in which we have achieved a quite good reproducibility. The design of the experiment is very simple. We have performed gas loading experiment, electrochemical experiments, and experiments of electromigration within palladium. Well, I am starting with gas loading experiment. This is this transparency is illustrating the experimental approach for gas loading. The experiments were performed by an isochoric method in which the temperature was driving the absorption and the desorption process. The samples were constituted by palladium rhodium alloy of 2 for 3 centimeters of dimension and thickness from 0.2 to 0.5 millimeters, which were set inside the reaction chamber, which was constituted by a tube of quartz. The samples were annealed at 900 degrees, cleaned by reaction with hydrogen, with deuterium at 900 degrees, evacuated, and then a deuterium pressure was allowed to enter the reaction chamber. In the meantime, the temperature was slowly decreased from 900 degrees till room temperature in about 30 hours. We were measuring the absorption from the pressure, from the decrease of pressure. Clearly, we were before making some blank experiments for measuring the absorption of the system due to the drop of temperature. By reverting the temperature, we could measure the decomposition of the sample. These plots are showing the experiment. As the temperature was decreasing, we had an absorption at high temperature at about 500 degrees, a decrease of the absorption, another absorption at about 100 degrees, and the most of the absorption was around 30 degrees. When we were heating the sample, we had the decomposition. The absorption patterns are described the hysteresis typical of the system. The experiment was sampled by a scintillation spectrometer, which was placed out of the reaction chamber at about 30 centimeters of distance and was also maintained at the same temperature by a fan. Before measuring the neutron emission, we performed blank experiments to have an idea of the background in the day preceding the experiments and the day following the experiments. Practically, the background was achieved by sampling any 10 minutes the background and measuring from this number of samples the average frequency and the maximum scattering from this frequency. Since we were never observing a scattering higher than 3 standard deviations, when we have performed the experiment, we have considered only the emission which was in excess of 3 standard deviations. And so, this is a typical experiment in the arrow in this direction is indicating the absorption. We measured emission since the highest temperature. Afterwards, large emission was measured in correspondence with most of the absorption when the stable phases were going to be formed, some degrees before the full stability range of the palladium alloy deuterium system. During the decomposition, we had again emission at before of the full decomposition of the sample. And we are in fact seeing that also this process is underlying the hysteresis seen in the absorption-desorption pattern. And we had again a high temperature emission. With other samples, we could reproduce, and we had 100% of reproductivity in the formation at a low temperature and in the decomposition at high temperature, decomposition of alpha plus beta phases of the deuterite. Now we are considering electrochemical experiments. First of all, we have performed some experiments, practical electrochemical experiment, to assess the absorption of deuterium within the alloy. And here we have performed the experiment at 25 degrees and 90 degrees. And we have changed the electrolyte, the concentration of the electrolyte, and the loading time, the potential. Well, practically we see, if we are considering the deuterium to metal atom ratio, that the main parameter which is increasing the absorption is the concentration of the electrolyte. In fact, when we are going from 0.1 molar lithium hydroxide to 0.5 molar lithium hydroxide, we saw an increase of the loading, which we ascribe just to the electrochemistry of the system. The system is more reversible at higher concentration of electrolyte. This trend was reproduced at 90 degrees. We see here that at 90 degrees, under the force absorption caused by the electrochemical pressure, we can maintain a high concentration of deuterium within the sample also at 90 degrees. We are now considering the experimental assemblement which was used for detecting neutrons during the electrochemical experiment. The detector is, as usual, an E213 scintillator of a large size, so the cell could be just placed inside the detector. The cell was suitable to have a thermostatic control from 25 degrees to 90 degrees. We were using again as a sample sheets of dimension 243 and thickness from 0.5 to 1 millimeter. The choice is important because we were just adapting the dimension and the weight of the sample to the current which we were using in loading. The point is that we were trying to achieve the full conversion of the sample into beta deuteride within 24 hours. Because just during the conversion of the sample, we were always measuring a neutron emission. Furthermore, we were using several conditions for neutron emission. Here I have put the conditions of 4 electrochemical experiments which were lasting a couple of months each one. The type of electrodes, the electrolytes, the dimension, and the condition of a neutron detection. Practically, we were measuring the neutrons, possible neutron emission, in a range which was varying from experiment to another experiment. And in any case, we were using some gates so we could discriminate a narrow of higher energy from a range of lower energy. For instance, here, the high energy range was from 1.445 to 1.85 energy. The total range was from 0.9 1.85. Clearly, there is an approximation in these numbers. The approximation is surely larger, about 20% for the lower energy threshold. And there is also an approximation in the efficiency, which we have estimated at about 30%, the uncertainty about these values. Now we are considering the first experiment. In the first experiment, we have used this sample, and the sample was loaded with a current of 150 milliamperes, about between 10 and 15 milliampere per square centimeters. Anyway, we were measuring the background without the cell in the neutron detector, and we have achieved this number of counts in the wall range and this number of counts in the high energy range. As we were putting the cell inside, we were measuring an increase in the high energy range, whereas the total counts were about the same level. We were learning in subsequent time that the cell is having a shadow effect on the background. We will see in the next experiments. After this emission, which was about 2 sigma about the background, the number of counts was going down to background level. Another experiment. Here I'm reporting the current program. Here we are reporting the frequency. All the neutron counts were made on the basis of 24 hours. At the beginning, we were achieving for a couple of days the background with the cell inside the spectrometer, but without no current. That is the cell open circuit. As we were putting the current across the cell, we had the frequency, which was increasing. And after a couple of days, the frequency was going down to the background level. With this experiment, after a couple of months, in which we have tried the change of temperature, change of currents, and so on, if we are in time or possibly in front of the poster, we could discuss the system. After a couple of months, we start a different type of experiment. The electrode which we charged at this date was discharged by anodic oxidation, and afterwards the frequency was measured in the neutron frequency was measured in open circuit condition. Afterwards, it was charged again by applying a constant current. The frequency was measured here, and the electrode was then discharged again. We considered the background the day in which the electrode was empty, in open condition. Reaction time, the time in which it was loaded, and background again, the time in which it was discharged. On repeating this experiment, we were able to see that as concerned the high frequency range, we were always positive. Only once we were within the standard deviation. And in fact, by summing up all the data, we had 4 standard deviations. Increase above the background measured either taking all the systems in open circuit condition or the condition in which the electrode was discharged. In fact, the background measuring in each condition, open circuit, or in the condition of discharge was fitting within 1%, even if the measurements were made delayed in the time in which the background was changed. The same was happening as concerned as the total energy, provided that the neutron detection was not extended to the low energy range, where the background increases about 1 order of magnitude, and so the signal, which is small, is digging inside the background. We can be accounted of this fact if we are considering the proton recoil spectrum for several energy. We see if we are putting a cut at about could be 1 MeV, we have a background which is a lot lower than the background when we have the full scale of the instrument. Experiments of this type were repeated also with palladium-silver alloy, increasing the range of energy in which we were performing our detection. Open circuit condition, background, as the current was crossing the cell, we had an increase in both the energy range. After the conversion in the beta physics, we have a drop to background level. Another experiment with a thicker electrode of palladium-rhodium alloy. This is a background in open, without the cell. With the cell in open circuit condition, there is clearly the shadow effect of the cell on the background. After we were applying current, and since the electrode is of a larger size, we had emission for a longer time. And here we can clearly see for the first time that we had indeed emission at energy above the 2.45 MeV predicted for DD reaction. Another way to see the emission of neutrons is to apply thermal perturbation to the cell. On the upper side of this figure, I'm reporting the temperature change which were applied to the cell. We see that from this frequency, as the temperature was increased, we had a decrease of the neutron frequency. As the temperature was decreased, the frequency was coming back to the original level, which means that before applying the temperature perturbation, indeed the cell was putting out some neutrons, but we were not able to detect because we had no reference to the actual background. On repeating several times, the behavior was reproduced. We checked at the end by discharging the cell, taking out by anodic oxidation deuterium from the electrode, if this was an artifact. And indeed it was not, because we could change the temperature, and indeed nothing was happening as concerns the reply of the scintillator. In the last point, we were charging again the electrode, and then discharging again. We had a small increase, about 1 standard deviation, but it was again for the 10th time we were charging an electrode, we had a neutron emission. We are now considering the third type of perturbation we were applying to palladium sheets. This figure is giving a schematic account of the design of the experiment. The sample was constituted by a strip of palladium, thin about 50 microns, wide 2 millimeters, and the length was about 10 centimeters. This was assembled inside this holder. The holder was having gold contacts in these 3 points. The sample was placed inside a closed vessel in which we could apply a pressure of deuterium so that the sample could absorb deuterium. In the meantime, by making a current to flow from this point to this point, the sample could be, once it was charged by deuterium, submitted to phenomena of electromigration of deuterium without the sample. And we could also sample the potential difference in these several points, so to have the resistance of this section, and all the length of the sample. In this further design, one side of the sample could be submitted to another electrostatic external field, part of the sample. In practice, we were putting here another electrode which was separated from the sample by mica insulator. Well, the background was measured in this condition before having deuterium inside the sample. And in fact, we observed a rather smooth background. Maximum deviation on sample of 10 minutes were about 3 sigma, about the average. As the current was flowing in the sample, as the sample was loaded, we had a significant increase of a neutron. The average emission which we could compute from this experiment was about 30 neutrons per second, which were lasting for all the time the current was flowing across the sample. Well, there is a point to be noted. When we were performing this experiment, from the resistance, from the variation of the resistance of the sample with respect to the original specimen of palladium, we could calculate that the loading of deuterium within the sample was not higher than the atom ratio not higher than 0.5 and 0.6. which means that we were achieving a significant neutron emission from a relatively low loading of the sample. This type of experiment was reproduced many times, and here in this table I'm comparing the frequency of the system when no deuterium was inside the sample, and the frequency was this. And the several experiments with deuterium in which we made other perturbations, temperature perturbation and vacuum application. Well, we see that in any case we have strong increase above the frequency of the background. Since the experiment could last for several days, several million neutrons were coming out from the experiment. When temperature was increased, the frequency was increasing, which seems that effectively temperature has a positive feedback on the reaction, or at least the increase of the resistance caused by the temperature is causing the electric field acting on the deuterium in the sample, and so increasing the effect of neutron emission correlated with electron migration. When vacuum was applied to the sample, we have again an increase. This may be explained as a consequence of Gorski effect, which is causing a stress to the sample. Well, if I have now to conclude, I would say that we were seeing neutron emission in several designs which corresponded to non-equilibrium situation. Well, non-equilibrium situation is a rather undefined word, because I cannot think that a sample which is submitted to a long electrolysis with bubbling of hydrogen, large over potential applied, is not in a non-equilibrium situation. I would say that this non-equilibrium really corresponds to a situation in which the deuterium inside the sample is in a dynamic situation. There is a drift which is superimposing to the normal kappa T motion of deuterium inside the sample. The last point which I want to outline is this. When we were measuring the increase of the resistance during the flow of the current inside the sample, which had been loaded by deuterium, when we were using the design in which part of the sample was submitted to an additional electrostatic field, we had that in the branch in which no additional electrostatic field was present, the concentration of deuterium was constant and not high. It was probably below 0.5, the atom ratio. On the contrary, in the branch of the sample in which we had the additional electrostatic field, we were observing this behavior, which shows that probably the sample was achieving a maximum of resistance corresponding to a loading about 0.7, 0.8. And after we were observing the decrease, which is generally associated to a further increase in the stoichiometry of the sample. Well, notwithstanding this fact, if it is true clearly, we were not observing an increase in the neutron emission from the sample. which means that as neutron emission is concerned, is not the high loading, which is the reason, the driving force of the emission, but is really a drift, a dynamic state of the deuterium. Clearly, this is not a theory. This is just an experimental observation. Thank you for your attention.
Thank you, Dr. Maynard. Time for any questions?
Let me know that in your observations, the foreground neutron count foreground
In my
foreground with cell, and so the background without cell. Is it true?
sorry, I have not understood. My background, what was?
Is your baseline is with the cell in place
Yeah.
or not in place?
No, I have shown experiments in which the background was taken without the cell, and so the background is larger. When I put in the cell open circuit, the background is decreasing because there is the old heavy water.
So I
in the
have
cell.
a comment.
Yes.
For more precise discussion, you should beat the cell without heavy water or current.
Yes, he has that.
Yeah.
Okay.
Yes, I will show. I have shown before.
Okay.
Yes, could you tell us what potential you were applying? What was the amplitude of the electrostatic potential applied at the end of?
You mean when we were applying? You mean the potential of electrolysis?
No.
The potential when we were applying? Okay, from 500 to 1,000 volts. But I must say that the effect of having this increasing absorption, we are explaining as an increasing absorption caused by the electric field, is rather independent from the magnitude of the field, and also from the sign, you know, because probably you are inducing on the other face of the application. Li abbiamo pubblicati
no, allo stesso modo, ce ne sono di meno.
Guarda, come energia abbiamo ancora da fare, come energia.
I'm going to present our experimental results on gas release experiments from deuterated palladium with high loading ratio. Contents of my presentation as follows. At first, we will mention about the objective of our study. The second, we will explain about the experimental procedure and the preparation of a PD sample and the measurement system. And then we will describe some examples from our positive results. First one is on neutron emission induced by deuterium gas release. In the second example, we will explain about DT gas breeding, deuterium production, and X-ray detection. And second, we will discuss on the correlation between DT gas and D by PD, and relation between DT gas breeding and the diffusion process of deuterium atom in palladium. Many papers indicating that nuclear reactions must occur in deuterated palladium are presented since the announcement of Dr. Fleischmann and Pons in 1989. It's very fascinating phenomenon because it has possibilities of being a new technology if we control of nuclear reactions in solid states. However, at present, we have much uncertainty on the mechanism of cold fusion phenomena. Objective of our study is clarification of the mechanism and key factors of this phenomenon. The authors assume that key factors to induce anomalous effects are as follows. First point is a high D/PD ratio. This factor is widely recognized as an important factor to cause nuclear effects. Second is the diffusion process of deuterium atoms. In order to clarify these effects of these factors, we've performed the following experiments. Our experiments consist of combined two parts. First part is the gas release experiments presented in ICCF-4. The aim of these experiments is to induce anomalous effects by the diffusion of deuterium atoms by heating a deuterated palladium. Second part is the sample preparation of deuterated palladium with a high D/PD ratio by electrochemical loading. And combining these two parts, we perform gas release experiments under vacuum condition using deuterated palladium with high loading ratio. Experimental procedure is as follows. At first, a high D/PD deuterated palladium samples is prepared by electrochemical loading. The second, the sample is electroplated by copper for the purpose of preventing release of deuterium gas. D/PD ratio is estimated by mass change of the sample measured by this balance. The sample is introduced into the vacuum chamber and set on a heater set on a heater. Evacuating the chamber, we heat the sample by this heater up to about 120 degrees centigrade. And then we observe nuclear products from the sample by these detectors. Here is a procedure of preparation of deuterated palladium. PD rod is 3 millimeter in diameter and 25 millimeter in length. We heat the palladium rod for 2 hours in the air at 90 degrees centigrade, and the sample is quenched in pure water. Electrochemical method is applied to deuterium loading into palladium. Usually, D/PD ratios that ranges from 0.7 to 0.83 is obtained. Of course, it is higher than D/PD ratio by gas loading. Next, the sample is electroplated by copper not to escape the deuterium atoms in palladium. Experimental devices are constituted as shown in this figure. The palladium sample, after loading, is introduced into this vacuum chamber. The vacuum chamber is evacuated by a turbomolecular pump. The 2 helium-3 detectors with polyethylene modulators are used for neutron counting. These are the silicon surface barrier detectors for charged particle spectroscopy. Cadmium, tellurium, and NI detectors are applied to X-ray and gamma-ray spectroscopy, respectively. Quadrupole mass spectrometer is used for gas analysis. And all nuclear measurement systems are electrically isolated from the other devices by using a stabilized power source. These are the photos of our experimental system. This is a vacuum chamber with the detectors. And these apparatus are, here is a measuring system for nuclear counting and spectroscopy. These apparatus are located in a clean room where temperature and humidity are always controlled at constant level. Let us move on to the experimental results. Here is a view graph which illustrates neutron emission induced by deuterium gas release by heating. In this figure, horizontal axis mean time and the vertical axis mean neutron complex. And this axis means heater temperature. d by PD of this sample is 0.71. At first, the heater temperature equal to room temperature. So we can see only background counting, neutron counting here. At this point, the heater was switched on. Since the temperature of the sample became to 100 degrees centigrade, that is about 400 Kelvin, deuterium gas released rapidly at this point. Simultaneously, we observe a clear neutron emission peak as shown here. We mainly watch the behavior of mass number 5 gas by mass spectrometer. Generally speaking, mass number 5 gas detected by quadrupole mass spectrometer consists of DT and DDH+. DDH+ is created by electron attack of a filament of humus. The number of DDH is determined by partial pressure of H and D. This is the data of DDH formation in our vacuum chamber. Horizontal axis means the total pressure and vertical ion current. We define DT gas breathing ratio, the ratio of mass number 5 ion current to DDH+ ion current. If DT gas breathing ratio is larger than 1.0, we are able to consider that DT gas is generated. With using the breathing ratio, we can demonstrate tritium production detected by mass spectrometer. Horizontal axis mean time, and the vertical axis pressure and DT gas breathing ratio. D by PD ratio of this sample is 0.83. At the beginning of evacuation, DT gas breathing ratio is 1.0. However, we see that DT gas breathing ratio increases gradually, as shown here. At this time, it is considered that deuterium atoms in palladium diffuse toward outside. Since the deuterium pressure gradient between inside and outside of the sample exists. Simultaneously, we observed X-ray emission, as mentioned later. At this point, we start the heating the sample up to 120 degrees centigrade, and then deuterium gas is released as shown here. DD gas breathing ratio increases simultaneously. We think the tritium atoms are produced during gas release by heating. This is X-ray emissions data. This is energy spectra for X-ray detection. In upper figure, an energy spectrum during period 1. The period 1 means this just after the beginning of evacuation. And the lower energy spectra, period 2, correspond to this period. These data is obtained for 5 minutes data. It is considered, we see the X-rays around 21 kilo electron volt radiated from the deuterium palladium sample. It is considered that detected X-rays attribute to the K-alpha characteristic X-ray of palladium. Let's move on to the discussion. We observed tritium production with high reproducibility. Then we summarize the relation between loading ratio d by PD and DD gas breathing ratio. In these figures, DD gas breathing ratios are evaluated at 10 to 5th tall after heating. It is considered that DD gas breathing ratio tends to increase as D by PD increases. Therefore, it seems that DD gas breathing ratio is related to D by PD. Next discussion. Here is a figure that illustrates the relation between degassing rate and DD gas breathing ratio. The degassing rate is defined by this pressure equation as shown here. Q is the degassing rate, and V is the chamber volume, and P is the pressure of the chamber, and S is net pumping speed. You see that DD gas breathing ratio increases as the degassing rate increases, and saturated at the certain value. At present, it is difficult to explain this data in detail. However, degassing rate has a certain relationship with the diffusion process of D atoms. Therefore, at least it can be said that tritium production is related to the diffusion process of deuterium atom in palladium. In concluding, I'd like to mention about concluding remarks. One, we performed gas release experiments under vacuum condition with high D by PD samples obtained by electrochemical loading. Two, we observed neutron emissions, X-ray emissions several times, and tritium productions with high reproducibility. Three, DD gas breathing ratio is related to D by PD and diffusion process of deuterium atoms. Thank you for your attention.
Could you speculate as to what is causing the 21 keV K alpha? Is it protons or is it something else?
This data?
The 21 keV K alpha, what is causing it?
Why this?
What mechanism?
ね、電子かプロトンか何が21ケボになる
I think it is I think the electron attack the palladium and characteristic X-ray produce. I think.
No, but you had a surface barrier detector and you did not mention about any charged particles.
Okay, I understand. We have surface barrier detectors and cadmium tellurium detectors, and this X-ray data obtained by these detectors, and no.
21ケボのケーク星を作っているのは何だと思ってるかってですアルジュブの中でだから電子なのか、イオンなのか
I think electron.
He thinks electrons.
Yes.
Well, he doesn't know.
But I don't know exactly.
Could you discriminate between the superposition of the two peaks at mass 5 by working at a different electron energy of the ionization? I mean, there is any possibility to work in a range which will produce DT plus, but not HDD?
HDD.
DDH かね、DT かっていうのをどういうふうにしてはっきりと合ってるか
I will show you this data. This is data for gas analysis obtained by our experiment. This is horizontal axis mass number and ion count for release gas. It is the data for loading gas. D2 gas is the spectrum. And this one is obtained by the gas during heating. So we can specify the DT gas breeding.
Well, I was meaning if you can have in your spectra only DT and not DDH by working in a different electron energy of the ionization of the electrons. You have an ion source with electrons that are ionizing your molecules. Sometimes you can discriminate. I don't know about these two molecules. If you can produce only DT and not DDH, I'm only wondering about that. Sometimes you can, sometimes you can't. It depends from the potential ionization of the two species. That is,
well, your comment.
I don't have to go.
Yes.
Comment. A loading value of 0.83 seems to be near the peak of your tritium production. And there's a poster out this afternoon session of a model that predicts that 0.83 is about exactly the peak of the tritium production. And you might want to take a look at that. It's kind of interesting. The reason I know it's in my model.
Thank you. Thank you very much.
Any other questions or comments? Yes. No, over there.
It's a very impressive.
Yes.
You are saying that the high loss ratio is realized by applying electrolysis and copper plating. But loading ratio for 0.7 or 0.83 is not so high. So is it because some hydrogen is lost while you are electroplating?
Yes. We say high loading ratio compared to the gas loading, 0.66.
I know this, but
要するにかなり好きっていうのはね、その 0.77 程度だったら逃げることもないのになんでカッパのコーティングなんかするか。
You're saying that it is not necessary copper coating?
No. While you are plating by copper, some utility may escape.
Yeah.
And then eventually the resultant loading ratio could be lower than that obtained when electrolysis is going on.
But exactly what do you want to know?
That's why I would like to know the reason why the loading is so low, even if you apply electrolysis.
Our aim is not to get a high loading ratio. Our aim of our study is not get the high loading ratio. So I think
A higher loading ratio would give you less tritium production.
Okay, last question.
Yeah. It's a very impressive paper, and I ask not in criticism, but did you look at the sample of palladium and evaporate it and make sure there was no tritium in the palladium to begin with, number one? And number two, was your D2O free of tritium oxide?
tritium oxide.
要するにトリチウムが初めからないということをちゃんと確認して言ってくださいというコメントだけです。
Thank you.
Thank you very much. We'll proceed. Next speaker.
He asked him was the sample.
Yes, but we don't have time. Yes or no? Yes or no?
I check the tritium contamination before experiment, and this data is for PDH. It was loaded with hydrogen, and there was no increase tritium breeding ratio. So we think.
Well, thank you very much. Let's proceed to the next speaker.
Dr. Samgin has some difficulties with English, so I will translate.
Значит, в этом докладе будут изложены результаты многолетних исследований, которые наша группа ведет применительно к системам твердый электролит критерий.
Group led by Dr. Samgin conducted in the Institute of High Temperature Electrochemistry, Russian Academy of Science, and focus of their research is solid electrolytes.
С 1989 года мы занимались исследованием суперионных кристаллов электрохимически насыщенных дейтерием.
Since 1989, this group was working with superionic crystals. What?
On the other side.
Oh, other side? So this group was working with superionic crystals saturated by deuterium.
В частности, мы занимались исследованием оксидных бронз, электрохимически насыщенных дейтерием.
This group started with bronze, tungsten oxides saturated by deuterium.
И затем в течение последних 3 лет, учитывая некоторые трудности, возникшие с бронзами и специфику нашего института, мы занялись исследованием высокотемпературных протон-проводящих электролитов.
And because there was technological problems with bronze, tungsten, monocrystals, it was made decision to switch attention to solid electrolytes.
В частности, последние 3 года занимались исследованием протон-проводящих электролитов на основе цератов стронция.
And last 3 years, this group was working with proton conductive electrolytes based on strontium cerate.
Промежуточные результаты этих исследований были доложены на Гавайской конференции.
Intermediate results of this research were presented in Hawaiian conference.
И Определенную уверенность в том, что мы были на правильном пути, у нас вызвал доклад доктора Мицуна, который был посвящен также этой теме, использованию цератов стронция.
And it was a nice surprise to find that this choice of research field was right, because in Hawaii was made a remarkable report by Dr. Mizuna.
Однако у нас были некоторые отличия от работ доктора Мицуна.
However, Dr. Sangin's approach has specific differences from
В частности, насколько мы поняли, доктор Мицуна работал в области температур до 400 градусов, когда протонная проводимость только появляется.
And specifically, Dr. Mizuna working in temperature range up to 400 centigrade when just proton conductance just appears.
И мы работали в более широкой области температур до 1000 градусов.
We are working in wider range up to 1000 centigrade.
В частности, в последнее время мы много внимания уделяли таким проблемам, как образованию сэндвич-структур, поскольку сами электролиты нельзя использовать, нужно использовать вместе с ними палладиевые электроды, а эти проблемы при высоких температурах являются очень серьезными.
Such wide temperature range is possible because of unique technology developed by this group in creation of electron conductive electrodes around on proton ceramic surface. And this is the biggest problem for proton conductive technology because of spill off electrodes during high temperature processes.
Другим отличием от доктора Мицуна было то, что мы параллельно мерили радиоактивное излучение.
Another difference is that it was measured not just calorimetric. It was not just calorimetric measurement, but also neutron measurement. And this picture represents experimental installation.
Показана наша электрохимическая ячейка с твердым электролитом, которая помещается в защитный домик.
And this cell is installed in protective house from boron impregnated polyethylene.
И она окружена двухкольцевым детектором.
Cell is surrounded by
То есть мы меряем 4π угол.
Neutron detector. So they measuring 4π angle.
На этом слайде показан сам электролит. Вот это протон-проводящая керамика и палладиевые или платиновые электроды.
So number one is solid electrolyte, and you can see electrodes, and sometimes from palladium or platinum, and sometimes it was used few tablets.
С помощью крейта камок и ядерной электроники все результаты заводились в IBM. Вот типичный метод. Typical method. Значит, протон-проводящий электролит следующего состава.
Proton conductor.
У него были палладиевые или платиновые электроды.
It was supplied by two platinum or palladium electrodes.
Электролит был допирован диспрозием или неодимом.
Was doped by dysprosium or neodymium.
Все это помещалось в атмосферу дейтерия или водорода.
This sandwich was installed in atmosphere of deuterium or hydrogen.
Затем было 4 этапа экспериментов, которые в общей сложности длились несколько дней.
4 steps, experimental steps, which usually took about a few days.
Сначала прикладывалось постоянное напряжение.
Сначала нагреть там?
Нет. Да. Сначала нагревалось до определенной температуры, когда появлялась протонная проводимость.
First of all, sample was heated up to certain temperature when proton conductance.
Затем прикладывался постоянный потенциал.
Then was applied current constant potential.
Затем с помощью специального электронного устройства мы прикладывали переменный импульсный потенциал.
Then a special electronic switch applied reversible electrical potential.
И последняя стадия это было термоциклирование.
And last stage include thermocycling.
Вот результаты сначала по калориметрии положительных экспериментов.
This results, first of all, about calorimetry. This is positive results obtained.
Вот это что касается экспериментов с постоянным током.
This data about constant current.
И с переменным.
And this is with reversible.
При разных потенциалах,
with different,
подаваемых на электроды.
Voltage supplied to electrodes.
Избытки тепла, которые нами были обнаружены,
And excess heat which was discovered,
при постоянном токе составляли десятки процентов.
with constant current was just
При переменном
10%,
наблюдались положительных
reversible
экспериментов
was
несколько сотен процентов.
few hundreds %.
Да. Параллельно мы измеряли во всех экспериментах нейтронное излучение. В экспериментах с дейтрон-проводящими твердыми электролитами были зафиксированы нейтронные вспышки.
In most experiments with deuterium were observed neutron bursts.
Что они себя представляли?
And this burst represents itself.
Но сразу же я хочу сказать, что нейтроны с теплом в принципе не коррелировали.
What was found that, first of all, that neutron burst not correlated to heat events.
Наша аппаратура позволяла регистрировать одновременно амплитудные спектры.
Our equipment allows simultaneously
затем временное распределение событий.
Amplitude spectrum and time
и также
distribution
событий нейтронов.
Events.
И также каждый раз мы измеряли временное распределение последовательности двух зарегистрированных нейтронных импульсов.
It also was measured time distribution of two consequent neutron events.
В экспериментах, где было обнаружено избыточное тепловыделение с использованием дейтерия,
experiments where was observed heat production,
были обнаружены нейтронные сигналы.
Neutron signals.
Это были единичные события.
It was single events.
Единичные события, которые длились, возможно, больше, имели длительность более 100 или порядка микросекунд.
And these events were continued for 100 or 1 millisecond.
Время разрешения нашей установки было 4 микросекунды.
Resolution time of installation is 4 nanoseconds.
Вот здесь приводится распечатка с экрана компьютера.
And this is just a picture from computer screen.
Где показана вот одна такая нейтронная вспышка.
Вот
это бэкграунд, фон.
Neutron burst.
Вот это
фон.
И вот это вот, значит, единичная нейтронная вспышка.
This is single neutron burst.
При анализе этих данных мы использовали только ту среднюю часть амплитудного спектра.
During analysis of this data was used only medium interval of this spectrum.
Чтобы отсечь возможные наводки электрические, а также от гамма-излучения и так далее.
Influence of any possible error of measurement.
В частности, вот обычно фон, вот здесь показаны результаты по двум кольцам. Одно кольцо и второе кольцо детектора. Внутреннее и внешнее.
Internal and external.
Обычно число событий было, когда фон 2, например, и 3.
This is background 2 or 3.
И никогда больше 7-8.
And never happened that it was more than 7 or 8.
Однако иногда наблюдались события, которые составляли 11 отсчетов.
And very rare were events
за интервал времени 16 секунд.
11 counts for 16 seconds.
Аппаратура также фиксировала время прихода этих событий.
And installation also monitor time of occurrence.
Отсюда мы могли заключить, что эти события иногда были очень кратковременными во времени, то есть действительно сотни микросекунд.
According to this, we could conclude that these events were very short.
Наконец, результаты общие. Общие. При использовании дейтерон проводящих электролитов.
When we used deuterium conducting electrolytes.
Нами наблюдалось избыточное тепловыделение
positive heat production
при постоянном токе, реверсивном и при термоциклировании.
Constant current, reverse current and thermocycling.
Также наблюдались единичные нейтронные события.
Also were observed single neutron bursts.
При использовании протон-проводящих электролитов
When proton conductive
при постоянном
electrolytes,
нейтронов не было никогда.
proton conductive electrolytes means that it was used hydrogen atmosphere. And so it was never observed neutron events.
Тепло при постоянном токе тоже никогда избытков тепла не наблюдалось. Однако, это пока мы не можем объяснить, тепло наблюдалось при реверсивном токе. Но оно имело две особенности. Во-первых, оно было меньше, чем при дейтерии. И второе, оно быстрее уменьшалось во времени. Если проанализировать все эксперименты, которые проводились в течение последнего года, после Гавайев, то избыток тепла можно уложить вот такие пределы, от 10 до 1000%, в зависимости от загрузки тока. Проведенные исследования по микрокалориметрии, в частности с использованием микрокалориметра КальВ,
were done microcalorimetric research with microcalorimeter CalV.
И также с помощью измерения электропроводности
and by measuring of electrical conductance.
Были обнаружен неизвестный ранее в литературе фазовый переход в системе твердый электролит дейтерий.
Transaction in this system.
Приблизительно в районе вот таком 450 градусов. И как раз где-то вокруг этого перехода мы обычно и ходили.
Usually near this phase transaction experiments were performed.
Вопрос о природе этого тепла таким образом остается открытым.
So it is impossible to talk about nature of this heat production yet.
Некоторые особенности также аномальные были обнаружены с помощью методов рентгенографии.
Also some abnormalities were discovered by method X-ray graphics.
Каждую керамику мы до и после эксперимента исследовали рентгеновскими лучами.
Before and after experiment were tested under X-rays.
И в частности в экспериментах, показавших наибольшие тепловые эффекты,
and in experiments which show larger heat events.
В некоторых таблетках были обнаружены расслоения фаз. В частности, появление фаз типа церио-2. Но это чисто предварительные пока результаты. Также следует отметить, что таблетки, показавшие положительные результаты, были покрыты многочисленными трещинами постоянно. Спасибо.
Demonstrate best results were covered by cracks. So that's all. Thank you very much.
Yes, please. Would you explain to us the voltage range in which was applied to the samples and the frequency of the reverse polarity? Or was it alternating current?
Напряжение, какие напряжения были использованы, какое время регрессировало, и частота.
Напряжение подавалось порядка от 10 до 40 вольт на электроды.
Voltage was used from 10 to 40 volts.
Обычно. Токи при этом составляли сотни микроампер или миллиампера.
Hundreds microamps or milliamps.
Частота реверсирования была разная, от сотых долей герца до герца.
Frequency of reversing were range from hundreds of hertz to hertz, single hertz.
Any other questions? Thank you very much.
Next presentation will be introduction from tungsten bronze.
Is it visible or no? I'll repeat. Thanks.
Much better.
Yeah. Thanks. Is it visible? My name is Ben Filimonov from Minsk, Belarus. I am a volunteer collaborator of Dr. Kabir Kaliyev from Yekaterinburg, Russia. We are carrying out joint experiments now in Dubna. Yes, and I am here to present our recent results on the neutron emission after deuterium loading of sodium, tungsten, bronzes. This work was started some years ago. It would be not necessary to present these results once more, but recently there appears some works with negative results that have done our previous work doubtful. So last year we carried out some tens of identical experiments of measuring neutron emission after deuterium loading of sodium, tungsten, bronzes, and presented it at the second Russian cold fusion conference. And I want to present them and discuss them here shortly. And after that, I'll present our recent results. Yeah. The experimental details were published earlier, so I'll say only a few words about it. Single crystals of sodium, tungsten, bronzes were treated with high voltage under high vacuum to remove some sodium from channels of conductivity of the tungsten bronze structure. Then they were loaded by gaseous deuterium, and neutron emission and some heat release was observed. Due to close correlation of neutron events with deuterium input and beginning of evacuation, we was able to summarize these results of many identical experiments taken as 0 point, a moment of deuterium input or a moment of beginning of evacuation. So the sum of about 50 identical results. Yes, as you can see, intensity of emission diminished from first minute to fifth minute, and then it is within background level. It is difference between counting rate and background rate with considering errors. This figure is similar that emission was stable, was durable, and decays slowly. It is not so. It is not so. In each experiment, there was a burst of emission of short durability, and not always the highest level of emission was at the first minute. It may be at the second minute, and the third, and the fourth, and so on, up to 10 minutes. Yes, but summarizing, we obtain such a plane curve, such a plane curve. Duration of emission above the background vary in experiment, and the average value was about 5 minutes. 5 minutes. It allowed us to do a preliminary conclusion that neutron events in sodium tungsten bronzes are connected somewhere with some slow processes. Supposedly, it is a diffusion of deuterium in thin surface layer of sodium tungsten bronzes, but it is not established reliably. Some events, as I have said, were observed at 10th minute and so on. It allowed us to concretize the experimental procedure for our recent experiments. Yes, if we consider the distribution of experiments, I recall it is about 50 experiments, on the signal background ratio, yes, we first can't obtain a plane curve when we enlarge the period of integration, the range of integration, we observed plane curve, and the average relation of signal to background is about 1.75. It means that the average reliability of single experiment is above 90%. It is not 100% as was reported earlier, but it is rather reliable. Yes. It is interesting that distribution of experiment on the ratio of the difference between signal and background to the error is not so plain, even if we integrate it in wide range. It has some appendix, and we are wonder what is it, and made a supposition that it is some deviation from experimental procedure, but maybe not from procedure, but some deviation in the nature of the crystals, because we tried to do all the experiment identical. Yes, and maybe next report of competitors group will confirm that supposition. Yes. I would be glad to stop at that point. Because it is rather clear